Hello, and welcome to Linear Algebra. This is lecture 8, and our topic today is properties of linear maps. So, last time, we talked about eigenvalues and eigenvectors of linear maps. So remember, this means that you have some non-zero vector, and the image of that non-zero vector under this linear map is a multiple of itself. In that case, we say that v is an eigenvector, and lambda is the corresponding eigenvalue. Okay, so this time, we want to say more about linear maps in general. So for example, let's start by noticing that if V and W are vector spaces, over a given field F, then LVW, the linear maps between V and W, is itself a vector space over this field. Right? So remember, a vector space is a set with a distinguished element, 0, and two operations, vector addition and scalar multiplication. So in this case, what are those? So vector addition, if you give me two linear maps between V and W, then I can add them and I get another linear map between V and W. All right, so of course we're adding them in the sense of functions. This is pointwise addition. The value that you assign to a given vector V is S of V plus T of V. And scalar multiplication well, if you give me a linear map and you give me an element of the field, then we just do scalar multiplication just like we did when we were talking about continuous functions. So this is pointwise multiplication. The value that this map assigns to a given vector V is just A times S of V. Right? And I'll let you check that with those two operations, the space of linear maps between V and W is a vector space. Right? The distinguished element, 0, is just the map that sends every vector in V to the 0 vector in W. Okay, but there's more you can do with linear maps. You can compose them. So let's say that U is another vector space over F. And suppose that we have a map S from U to V and a map T from V to W, linear maps. Then it makes sense to compose them, and we get a map that goes from U to W, and this is a linear map. Right? So let's check that. Remember that we have to check two things to know if something is a linear map. We have to check additivity and homogeneity, right? So additivity means that it sends vector addition to vector addition, and homogeneity means that it sends scalar multiplication to scalar multiplication, right? But I pointed out at the beginning of last lecture that you can actually check both of them at the same time. So a quick way of saying that is we just have to check that it sends linear combinations to linear combinations. So let's say that you pick two vectors in U and a scalar F. So what we need to check is that the image of this linear combination u1 plus a times u2 under T composed with S is the linear combination of the corresponding images, right? But that's easy to check because T composed with S, by definition, that just means this is T of S of U1 plus AU2, right? And I know that S is linear, so that means that I can write this as S of U1 plus A times S of U2. And then I know that T is linear, so I can write this as T of S of U1 plus A times T of S of U2. And that's exactly what we wanted. Okay. So you can compose. Also, you can invert. So suppose that T is now a linear map from a vector space to itself, and it is invertible. Right, just as a reminder, an invertible linear map we call an isomorphism. When you have an isomorphism from a space to itself, you can also call that an endomorphism. Okay, then so it has an inverse map. Sorry, let's do this more generally. I don't need for it to be from a space to itself. Let's go from V to W. So it's an isomorphism, not necessarily an endomorphism. So I have a map from V to W, and then we're going to take the inverse map, goes from W to V. And the claim is that this is also a linear map. That is, T inverse is in L from W to V. Okay, so let's check this. Well, just like we did a moment ago, to check whether or not a map is linear, what we need to check is that it takes linear combinations to linear combinations. Right? And it's enough to do linear combinations with two vectors and one constant. So let W1 and W2 be vectors in W and A an element of the field. We need to check that T inverse of W1 plus A times W2 is equal to T inverse of W1 plus A times T inverse of W2. Okay, so here's what we'll do. We'll start with this expression, and we'll apply T to it. So we have T of T inverse of W1 plus A times T inverse of W2. Okay, now because we know that T is linear, we know that this is equal to T of T inverse of W1 plus A times T of T inverse of W2. And now by definition, T of T inverse is just the identity. So we end up with just W1 plus A times W2. Right? Now apply T inverse to both sides of this equality. So the T inverse applied to T cancels out, so we end up with T inverse of W1 plus A times T inverse of W2. On the other hand, that's T inverse of W1 plus A times W2, and that's exactly what we needed to check. Okay, we also have the distributive loss, right? So if you do S composed with T1 plus T2, that's equal to S composed with T1 plus S composed with T2. And similarly, if you start out with S1 plus S2 and compose that with T, you end up with S1 composed with T plus S2 composed with T. Okay, however, in general, composition of linear maps is not a commutative, right? On the one hand, it's entirely possible for this left-hand side to make sense and the right-hand side not to make sense. For example, if we're in the situation above where S goes from U to V and T goes from V to W, then it makes sense to form the composition T composed with S. But there's no reason that for you to form S composed with T, right? Because W might be a completely different space from U. So S composed with T doesn't make sense. But that's not the only reason this can fail. So this is even when both make sense. And we'll see many, many, many examples where this, these two fail to be equal to each other. It turns out that the Heisenberg uncertainty principle can be expressed as an inequality where you're saying that the product of how well you know the position of a particle and how well you know the momentum of that particle is bounded below by the commutator of those two operators. So if you like, the Heisenberg uncertainty principle boils down to the fact that composition of linear operators is not commutative. If it were commutative, we wouldn't have the Heisenberg uncertainty principle and all of reality would collapse. So it's a really important fact. Okay, now I mentioned previously that matrix multiplication was in some sense the most important example of a linear map because linear maps end up reducing to matrix multiplication. So here is our first way of making sense of that. So for every linear map T between Fn and Fm, so this any field F, we're just looking at very particular vector spaces, Fn and Fm. There is one and only one matrix A of size m by n such that for every vector in Fn, the image of that vector under T is exactly what you get by matrix vector multiplication. Right? So every linear map between Fn and Fm is given by matrix vector multiplication. Right? So in this setting, we call the matrix of T, or we say that T is represented by A. Okay. Now the proof turns out to be very quick. Okay, and the reason is that let's say that you had a matrix and you're looking at matrix vector multiplication. We've seen how to find the columns of that matrix, right? So we know that A times EJ is equal to the jth column of A. So remember that EJ is the vector that has zeros in all of its positions except for the jth position where it has a 1, right? So we saw when we talked about matrix vector multiplication that you can think about a matrix vector product as taking a linear combination of the columns of A, where the coefficients are the entries of the vector V, right? In this case, the vector EJ just has zeros except for this one. So when you're taking this linear combination of the columns, you're not taking any contribution from any column except for the jth one, and you're just taking the whole jth column. So that's why this is true. You get the jth column of A. Okay, so since that's true, we know that if T of V is equal to A times V, then the jth column of A excuse me, would be T of EJ. So notice that proves uniqueness, right? Because if T of V is equal to A times V, then I can find the jth column as just T of EJ. So there can only be one matrix that satisfies this property. Now, to show that there is such a matrix, let's just define it. Let's define AJ to be T of EJ. And let's let the matrix A be the matrix whose columns are A1 up through AN. Let's keep zeros. Then note that for any vector V with entries V1 through Vn, okay, so T of V is equal to T of, well, this vector I can write as the linear combination of the EJs with coefficient Vj. Right, so this J goes from 1 to n. Now T is a linear map, so that means that it sends linear combinations to linear combinations. So I can write this as this linear combination of the T of EJs. Right, but now that's exactly how we defined AJ, right? And we've seen before that that's exactly the matrix vector product of A with V. But now notice what's happened. We start with an arbitrary vector, V, and we've seen that T of V is equal to A times V as long as you define the matrix A in this way, right? But that's exactly what we needed to show. Okay, so every linear map between Fn and Fm is given by multiplication by a matrix. Okay, let's look at an example. So here's one of those maps that we defined geometrically. So take R theta as the map from R2 to R2 that rotates around the origin counterclockwise by theta. Okay, so it's a linear map. It goes from R2 to R2. So we know that it's given by matrix vector multiplication. Let's call the matrix A sub theta. So we know that there's a 2 by 2 matrix with real coefficients such that R theta of a vector is equal to just take this matrix A theta and multiply with V, right? And we know that A sub theta, we know how to find it. We know it's going to have two columns, and the first column is just going to be R theta applied to E1, and the second column is going to be R theta applied to E2. Okay, so let's figure out what those are. So E1 is this vector, right? The 1, 0, right? So it's just a vector of length 1 along the x-axis. Now, I apply theta. I think that's too big. And I end up with a vector like this. So this is E1. This is r theta of E1. And so we just need to know what are the coordinates of this endpoint. Okay, but this is a right angle triangle, and this angle is theta. So we know these coordinates. This has coordinates cosine theta, sine theta. Okay, and similarly, if we have, here's the vector E2, and then I rotate it counterclockwise by theta to get r theta of E2. Okay, well, it's the same thing. To figure out the coordinates of this point, we just notice that this is a right angle triangle and that we already have this angle theta. So then it's easy to see that this has coordinates minus sine theta, cosine theta. Right? If you like, just because it's this triangle on its side. Okay, but putting these together, we see that the matrix A theta has first column cosine theta, sine theta, and its second column is minus sine theta, cosine theta. Okay, well, that means that we now have a formula for this geometric map, right? So we can say, hence for each vector xy in R2, we have r theta. So rotating a vector xy counterclockwise by an angle of theta is the same as just multiplying it by this matrix, cosine theta, sine theta, minus sine theta, cosine theta, applied to the vector xy. And if you do that, you end up with coordinates x cosine theta minus y sine theta, and then the other coordinate is x sine theta plus y cosine theta. Okay, excellent. So that's an example of starting with a linear map, find the matrix associated to it. Okay, so we've seen that every linear map between Fn and Fm is given by multiplication by a matrix of size m by n. On the other hand, both of those spaces, the linear maps between Fn and Fm, and the matrices of a given size, are vector spaces. So this identification of every linear map with multiplication by a matrix actually extends to, say, the set of linear maps between Fn and Fm, and the set of linear maps of matrices of size m by n are the same as vector spaces. They are isomorphic vector spaces. So let's write that down. As vector spaces, linear maps between Fn and Fm and matrices of size m by n are the same. And more formally, here's the theorem. So let's C be the map that takes a linear map from Fn to Fn and assigns to it the m by n matrix associated to it. So let this be the function which assigns to each linear map its matrix. Then the theorem is that C is a linear isomorphism. Okay, let's prove this. Okay, so I need to prove two things. I need to prove that this is linear, and I need to prove that it's an isomorphism. Okay, so the fact that it's an isomorphism is easy because the theorem we proved above, where we showed that every linear map is associated to a matrix, in particular showed that it was unique, right? So this map we already know is injective. It's easy to see that it's surjective. So we're just going to focus on showing that C is linear. Okay, so what we want to check is that if you give me two linear maps, and a scalar, then the matrix that I get from applying C to T1 plus A T2 is the same matrix, so let's say coincides with the matrix C of T1 plus A times C of T2. Okay, so I want to show that this matrix is the same as this matrix. And a fast way of doing that is to show that every column of this matrix is the same as the corresponding column of this matrix. So we can see this by noticing that their jth columns are, okay, so the jth column of this matrix is what you get from this linear map when you apply it to EJ. So this is T1 plus AT2 applied to EJ. And the jth column of this matrix is what I get by finding the jth column of this guy plus A times the jth column of this guy. And the jth column here is just what you get from applying this linear map to EJ. The jth column here is what I get from applying this map to the column, to the vector EJ. That is to say, that the jth column here is T1 of EJ plus A times T2 of EJ, right? And now these are the same. So which, these are the same because T1 and T2, right? Because the way addition is defined on linear maps, the sum applied to a vector is equal to apply the first one to that vector and add to it what you get by applying the second one to that vector. Okay, so they have the same jth column, so they are the same matrix. Okay, I want to point out also on the topic of more about linear maps that there are several linear maps you're already familiar with. Yeah, that's right. There are various linear maps you are familiar with from calculus. So for example, the derivative is a linear map. So here we're going to start with functions that have a derivative. So this is going to be all of the f in so, okay. Here, let's do this a little slower. The derivative is linear map. So let's let d of ab be all of those functions c of ab that are differentiable. And then C1 of AB is going to be all of those functions in D of AB, so they're differentiable, so that f prime is continuous. Then the derivative is a linear map from C1 of AB to C of AB. Remember, C of AB are those functions from defined between A and B that are continuous, right? Real valued functions. So what we're saying, D is a map from C1 of AB to C of AB, and it's a linear map, right? So remember, to check that something's a linear map, we just need to check that it takes linear combinations to linear combinations. So here, for any F1, F2 in C1 of AB, and any scalar, let's say lambda in the real numbers, we have the derivative of F1 plus lambda F2. So I want to identify what function this is. So let's see, what does it do to a point X? So this is, because it's just a derivative of this function, F1 plus lambda F2 prime evaluated at X. But the derivative of the sum is equal to the sum of the derivatives, while the derivative of a product satisfies the Leibniz rule. But if you have a constant, then the constant just comes out of the derivative. So that's lambda f2 prime of x, right? Which in other notation is just d of f1 plus lambda d of f2, all of that applied to x. So there we go. This is indeed a linear map. Another example, take any continuous function defined on AB, then the map multiplication by H is a linear map. From continuous functions to continuous functions. Right, so MH of function f is another function, so I have to tell you what it does to a point x. What it does is h of x times f of x, right? So I'll let you check that this is indeed a linear map. This one is a little more fun. We're going to take like a continuous linear combination. So what does that mean? So let's start with a function k from R2 to R that's continuous. Let's say we can define a linear map by integrating against k in one of its arguments. All right, so T sub k is going to be a map from continuous functions, say on AB, to continuous functions on AB. So what T of k is going to do to a function f is going to give you another function, so I have to tell you what that function does to a point. So the point x, we're going to assign the integral between a and b of k of x comma y, f of y, dy. Okay, so you can think of the integral as being like a continuous form of summing, and so we're just taking the values of f and we're taking a linear combination, sort of a continuous linear combination where our coefficients are given by this function k. Right, so in this setting, we say that K is the integral kernel of this map T sub K. Let's check that this is indeed a linear map. Okay, so to check that a map is linear, I have to check that it takes linear combinations to linear combinations. So let's take two vectors. In this case, the vectors are continuous functions defined on AB. And let's take a scalar. And then I have to check that what happens when I apply T sub K to F1 plus lambda F2. Right? So I'm going to get another function. Let's see what this function does to X. Right? Well, by definition, this is the integral between A and B of this integral kernel against this function. So I have F1 plus lambda F2 evaluated y dy. And well, that's equal to the integral of this kernel against F1 of y plus this kernel against lambda F2 of y dy. And then because integrals open up sums and pull out constants, I can write this as the integral from a to b of k of xy f1 of y dy plus lambda times the integral from a to b k of xy f2 of y dy. And that's exactly tk of f1 at x plus lambda times tk of f2 evaluated at x, right? Which shows that it's linear. Okay, so I've been talking about this as being like a continuous linear combination, but it's sort of more than that because it's a linear combination where the coefficients depend on x, right? So really, it's like a continuous version of matrix vector multiplication. So let's make that precise, right? So note that if we think of a vector, say with entries v1 through vn inside Rn as a function, right? So there's a simple way of thinking of a vector as a function. It's a function defined on the set of numbers 1 through n to the real numbers. Here, let's put a hat on this just to make it, just to distinguish it. So what this would do is v hat applied to j would be equal to v sub j, the jth entry, right? So you can think of this vector. Let's say you have the vector 4, 17 pi as a function from the set 1, 2, 3 to the real numbers. And it would assign to 1, it would assign 4, to 2 it would assign 17, to 3 it would assign pi, right? And it's just the first coordinate, second coordinate, third coordinate. So you can think of a vector like that. You can also think of a matrix in the same way. So if I give you a matrix A, and I say that its entries are Aij, then really what we're doing is we're saying, well, to every ij, where I is between 1 and m and j is between 1 and n, assign a real number. So let's think of this as a function. Let's use the hat notation again. A hat, where now you go from, it's just to each index. So I'm going from the set 1 through m cross 1 through n to the real numbers. Right, so this would be a hat of ij it's just little a ij. Then Okay, matrix vector multiplication, if we think of this as a function, it would assign to I, right? So this would be the sum aij vj, and j goes from 1 to n, which we could write as the sum of a hat I comma j v hat of j, where j goes from 1 to n, right? So notice that this is really like the linear map we had above. That was a continuous version of this, right? So we see matrix vector multiplication is just like the previous example. But replacing the interval with the set 1 through n, and replacing the integral with the sum. Right? But if you make those changes, then matrix vector multiplication is a particular kind of this map with an integral kernel. It turns out that linear maps in great generality can be given by integrals against an integral kernel. To make the class of maps you can represent as large as possible, you have to make the integral kernels that you're allowed to use as large as possible. But if you do that, you can get all the linear maps you could be interested in that way. As one final example, if we let f infinity be the maps from the natural numbers to f, so here, and the natural numbers is just the numbers you count with, 1, 2, the positive integers. So another way of thinking about this is be the space of infinite sequences in F. Okay, so this is a vector space, generalizing like Fn, right? It's just like letting n go to infinity. And let's define some linear maps. So for any natural number, define the kth shift map, right? So sk is going to go from f infinity to f infinity. So you're going to give me an infinite sequence. I'm going to give you back another infinite sequence, right? So sk applied to the sequence an, where n is greater than or equal to 1, is just the sequence an plus k, where n is greater than or equal to 1. So I just ignore the first k minus 1 terms and start with the kth plus 1. I'm going to ignore the first k terms and just start the sequence with the next one. Okay, these are all linear maps. Linear maps for every k. Okay, you can find many more examples in the book. All right, so that's where we'll stop for this lecture, and we'll pick it up from there next time.